My name is Ernest Rutherford, and in the spring of 1912, a young Dane arrived at my laboratory in Manchester with a problem I had created and could not solve. I had spent years proving that the atom had a nucleus, a tiny, dense, positively charged core at the center of almost nothing, surrounded by electrons circling at enormous distances, like planets around a sun. It was the most important discovery of my life, and it was broken. From the moment I proposed it, every physicist in Europe knew it could not work. Not because the nucleus was wrong. The nucleus was right. It was broken because of what the electrons would do next. That was what the young man from Copenhagen came to fix. He could not fix it. Not with any physics that existed. And he did it anyway. His name was Niels Bohr. He was 26 years old. And what he showed me in 1913 became the foundation of everything that followed. Quantum mechanics, the structure of every element, the reason chemistry works the way it does, the reason the sun burns, the reason your body holds together at all. He showed me something that cannot work, and it was right about everything. This is how it happened. Niels Bohr was born in Copenhagen on the 7th of October, 1885. His father, Christian Bohr, was a professor of physiology at the University of Copenhagen, and he was nominated twice for the Nobel Prize. He ran a household where science was not a subject, but a way of thinking. The dining table in the Bohr home was where ideas were argued, tested, and discarded. Niels grew up in that atmosphere before he had words for what it was. His brother Harold became a mathematician. He was also a member of the Danish national football team that won a silver medal at the 1908 Olympics in London. Niels played as well. The two brothers were inseparable, different in temperament, alike in the conviction that a problem worth solving was worth everything. Niels went to the University of Copenhagen in 1903. He took his doctorate in 1911. His thesis was on the electron theory of metals, a subject that already pointed toward the question that would define his life. How do electrons actually behave? Classical physics had answers. Bohr was already beginning to suspect they were wrong. In the autumn of 1911, he came to England. He spent several months at Cambridge, working in the Cavendish laboratory under J.J. Thomson, the man who had discovered the electron itself. The relationship did not flourish. Thomson's model of the atom, in which electrons were embedded in a sphere of positive charge like currants in a pudding, had already been overturned by my own experiments. Thomson was brilliant, but he was defending a model that no longer held. In the spring of 1912, Bohr moved to Manchester, to my laboratory. And that is where our story begins in earnest. What I had built was extraordinary, and it was failing from the moment it existed. In 1909, my students Hans Geiger and Ernest Marsden fired particles at a thin sheet of gold foil. Most particles went straight through, which was expected, but a small number, 1 in 8,000 roughly, bounced directly back. In Thomson's model, with charge spread across the entire atom, that was impossible. A particle that small, moving that fast, could not be deflected by something that diffused. I spent 2 years working out what it meant. My conclusion was this: almost all the mass of an atom is concentrated in an unimaginably small core at its center. The nucleus. The atom is almost entirely empty space. The electrons orbit this nucleus at a vast distance, the way planets orbit the sun. This was correct. We have not revised it since, but there was a problem I could not solve, and every physicist who read my paper in 1911 saw it immediately. According to classical physics, a charged particle moving in a circle must continuously give off energy, which means an electron circling a nucleus bleeds energy with every orbit. The orbit shrinks. The electron spirals inward and hits the nucleus. Calculations showed this should happen in roughly 100 millionths of a second. Every atom in the universe should collapse almost instantly. But you are made of atoms. The chair beneath you is made of atoms. The sun has been burning for 4.5 billion years. Atoms do not collapse. We know this because we exist. My model offered no explanation for why. That was the problem Niels Bohr arrived to solve. He worked in my laboratory through the spring of 1912. Quiet, methodical, unhurried. A man who thought before he spoke and meant everything he said. He left at the end of July 1912. He married Margrethe Norland on the 1st of August, but he took the problem with him. He took my broken model, and he asked a question no one had thought to ask. Not how do we fix the model within the rules of classical physics, but what if classical physics simply does not apply to the inside of an atom? What if, at that scale, the rules are different? Bohr looked at my atom and said, "Not here, not at this scale." He had been reading the work of Max Planck, who in 1900 had discovered that energy does not flow in a smooth stream. It comes in fixed packets, discrete amounts. Quanta. Bohr understood what this meant for the atom. He proposed something that, on its face, sounds impossible. Electrons, he said, can only occupy certain orbits around the nucleus. Not any orbit, but specific orbits, fixed in space, like rungs on a ladder. An electron can be on one rung or the next. It cannot be between them. There is no between, and while the electron stays on its rung, it does not radiate. It does not bleed energy. It simply orbits, silently, in defiance of everything classical physics demanded. When an electron jumps from a higher rung to a lower one, it releases a burst of energy, a single quantum of light. When it absorbs energy from outside, it jumps up. That is all. That is the mechanism. Steps, not slopes. Jumps, not spirals. There was no physical explanation for why the electron obeyed these rules. Bohr was not offering one. He was simply saying, this is what the electron does. And here are the consequences. He sent me his paper on the 6th of March, 1913. I read it in my office in Manchester. The equations were clean. The predictions were extraordinary. And the assumption, at the heart of it, that an electron could simply decide not to follow the laws of physics, violated everything I had spent my career defending. I wrote back on the 20th of March. My first line was direct. I told him this cannot work. I told him his work showed remarkable ingenuity and that his results seemed to agree very well with the experimental facts. But I also told him something that I could not let pass. I wrote, how does an electron decide what frequency it is going to vibrate at when it passes from one stationary state to the other? It seems to me that you would have to assume that the electron knows beforehand where it is going to stop. This was my objection, and I believe it was a fair one. In Bohr's model, the electron emits light of a specific frequency as it jumps between orbits. But the frequency of that light depends on the energy difference between the orbit it is leaving and the orbit it is arriving at, which means the electron must somehow know, before it jumps, exactly where it is going to land. It must choose its destination before it departs. How does an electron know anything? How does it decide? What does deciding even mean at that scale? I had no answer. Neither did Bohr. He sent me a long reply. He was courteous and precise and absolutely unmoved. My objection had no answer. Neither did anyone else's. The numbers were correct. For decades, scientists had observed that when hydrogen gas is heated, it emits light, but not all colors of light. Specific colors, specific wavelengths in a precise pattern. No one had ever explained why. The pattern was called the Balmer series, after the man who described it mathematically in 1885. But Balmer had found the pattern by fitting a formula to data. He had no theory. No one did. The lines of the hydrogen spectrum were simply there, like a fingerprint no one could identify. Bohr told me that a friend had mentioned the Balmer series to him early in 1913, asking how his new model would account for it. Bohr's reply, as he later recounted, was that he had not given it much thought. He believed the spectrum would be too complicated to address. Then he looked up Balmer's formula. He later told me that as soon as he saw Balmer's formula, the whole thing became immediately clear to him. Bohr's model, with its fixed orbits and quantum jumps, predicted every line in the Balmer series. Not approximately. Exactly. Every wavelength, calculated from first principles, matched the observed values with extraordinary precision. For the first time in the history of physics, a theoretical model had correctly derived the spectrum of an element from the underlying structure of the atom. I told the world, in public, what I believed. Bohr had faced the difficulties of atomic structure by bringing in the idea of the quantum.
At all events, something is going on which is inexplicable by the older mechanics. That was as far as I was willing to go. Inexplicable. I was 41 years old when I said it. I had already won a Nobel Prize. I had already overturned one model of the atom. I believed I understood how the world worked at its smallest scale. And here was a man 14 years younger than me, telling me that the laws I had spent my career applying simply did not hold inside the atom, and proving it with numbers I could not dispute. Not everyone was so measured in their response. Paul Ehrenfest, one of the finest theoretical physicists in Europe, wrote to a colleague that Bohr's work had driven him to despair. "If this is the way to reach the goal," he wrote, "I must give up doing physics." He did not give up. None of them did, because the numbers would not be argued with. Bohr received the Nobel Prize in Physics in 1922, 9 years after his first paper. He was 37 years old. He returned to Copenhagen and founded the Institute for Theoretical Physics in 1921. For the next 2 decades, it became the center of the quantum revolution. Heisenberg worked there. Pauli worked there. The deepest arguments about the nature of reality were argued in those rooms, in Danish and German and English, at all hours, by the most gifted physicists of the century. Bohr was at the center of all of it, not because he had answers, but because he knew how to hold open questions without needing to close them. Germany had occupied Denmark since April 1940. Bohr was half Jewish through his mother. In 1943, he was warned that his arrest was imminent. He escaped by boat to Sweden in the night, and from there flew to Britain crammed into the bomb bay of a military aircraft. He arrived in the United States and worked at Los Alamos, where the atomic bomb was being built. He spent much of his time arguing that the weapon would change everything, that nations must share knowledge or face catastrophe. Churchill spent most of their meeting berating him. Roosevelt was warmer, but nothing changed. He went home after the war. He continued to think, to write, to argue. On the 18th of November, 1962, Niels Bohr died in Copenhagen. He was 77 years old. His son, Oj, became a physicist. In 1975, Oj Bohr shared the Nobel Prize in Physics for his work on the structure of the atomic nucleus. Father and son. The same prize, 53 years apart. Think about what that model gave the world. Every chemistry textbook on Earth begins with a diagram of the Bohr atom. The nucleus in the center, the electron in its orbit, the arrow showing the quantum jump. It is the most reproduced scientific image in history. The reason lasers work, the reason nuclear power stations generate heat, the reason the periodic table is ordered the way it is, all of it traces back to the model that a 26-year-old built in 1913 in my city, using ideas that had no right to work. I remember the afternoon his first paper reached my desk in Manchester. The equations were clean, the predictions were extraordinary, and the assumptions at the heart of it, the fixed orbits, the quantum jumps, the electrons that somehow know where they are going, violated every mechanical principle I had spent my career defending. I told him it could not work. I was right about the mechanics. He, however, was correct about the atom. What I told him could not work became the foundation of everything that followed. Every element in the periodic table, every laser, every nuclear power station, the model that violated my laws became the basis of all of it. In the end, he was always right. That is the thing about the deepest truths in physics. They do not ask your permission. They do not wait for you to find them comfortable. They are simply there, fixed and patient, waiting for someone young enough not to know they are impossible. Niels Bohr was 26 years old when he arrived at my laboratory in Manchester in 1912. He had no proof that classical physics was wrong at the scale of the atom. He had a broken model,
a friend's passing remark about a formula, and the absolute clarity that came when he finally looked it up. The whole thing was immediately clear to him. He walked into my laboratory with a problem I had created. He left with the answer I could not find. And nothing in physics has been the same since.